Good day everyone! For our final group project assignments, we are required to make a video presenting our project, which consists of Task 1 and Task 2. Task 1 focuses on the application of first-order differential equations, while Task 2 focuses on the application of numerical methods. Before we begin, I will first introduce you to my group members.
Hi.
Nothing else makes me feel high.
In Task 1, we were required to analyze the population growth using differential equations. First, we collected secondary data of Japan's populations using reliable sources like Trends or the World Bank, covering a span of at least 20 years. Next, using this data, we derived a particular solution of differential equations model representing Japan's population growth. This model is based on the standard form shown in our reference materials. And we created two graphs using graphing tools like Desmos. After that, we used our equation to predict one future value and one past value. Lastly, we analyzed our data by comparing them with the actual data, calculating percentage errors, and discussing possible reasons for any differences. We also explored what factors that may have affected the past and what may influence the future.
To begin our analysis, we followed step 1 by gathering a reliable set of data. In this table, we present the population of Japan from the year 1990 to 2009, which gives us a 20-year span of data as required. We obtain this data from official and trusted sources, which is Trends, ensuring its accuracy and relevance for our project. The population figures are listed year by year, showing how Japan's population has steadily increased during this period from around 123.7 million in 1990 to 128.1 million in 2009. This dataset forms the foundation of our project, as it will be used to model and analyze population growth using differential equations in the next steps. Figure 1 presents a real data plot showing the actual recorded population of Japan from 1990 to 2009. The graph exhibits a generally increasing trend, with the population growing from approximately 123 million in 1990 to about 128 million in 2009. Figure 2 shows a particular solution graph representing a mathematical model or equation used to estimate or predict population growth over the same time frame. This graph appears exponential, indicating continuous growth without plateauing. While it may fit yearly growth well, it doesn't reflect the real life showing growth rate seen in the actual data in Figure 1. In Figure 3, we see a zoom-out graph showing the estimated population over a much larger time span. The red curve, based on an exponential equation, shows rapid and continuous growth. However, this wide view doesn't help us clearly observe how well the model fits the actual population data specifically from 1990 to 2009. That's where Figure 4 comes in. A zoom-in graph focuses precisely on 1990 to 2009. The green dots represent actual recorded population figures, while the red line is the estimated curve. Here we can see that the actual population rises more slowly and starts to level off, while the estimated curve continues to increase. Overall, while the model predicts general growth, it does not accurately capture Japan's slowing population trend from 1990 to 2009.
Since we have obtained our value of particular solution, next we use the value of particular solution in step 2 to predict the future and past value.
P is equals to 123,686,321 e to the power of 0.0031 t. We using one data from table. T is equals to 2, refer to 1992. To predict a future record of number of population in Japan, we set T is equals to 3, refer to 1993. To predict a past record of number of population in Japan, we set T is equals to 1, refer to 1991. Hence, we got the estimate future and the estimate past number of population in Japan.
Moving on to analysis and discussion. As you can see on the screen, the calculated value for the future value and the past value is not equivalent to the actual value. The two values do not differ significantly, despite the value calculated by using the particular solution not being equivalent to the actual value. We can demonstrate that in our next step where we calculated the percentage error. As a result, most of our data is accurate.
Next, we are going to calculate the percentage error.
By using percentage error formula, we use t is equals to 3, refer to 1993, to get percentage error for future value, and we obtain 0.05%. For past value, we use t is equals to 1, refer to 1991, and we obtain percentage error for past value is equals to 0.0029%.
From our observation, there is a difference between the actual value and the value calculated from the particular solution. Several factors and reasons contribute to the deviation in the data. The main reason of the difference is a real weight variation. The differential equation assumes perfect exponential decay, but in reality, many unpredictable factors such as immigration or emigration can affect the population. Japan experienced a post-World War II baby boom, especially during 1947 until 1948. This created a large generation that sustained population growth through the 20th century. Even when fertility started to decline in the 1970s, there were still enough people of childbearing age to keep the total population growing for a while. This is called population momentum. Another factor was higher birth rate in the past, although Japan's fertility rate started falling after the 1970s. In 1990s, the total fertility rate was around 1.54, while today it is around 1 to 26 or lower. Japan's population falls for 15 years in a row after 2010. Japan's population decreased by over 500,000 people, reaching 124.9 million as of January 1st, highlights the record low of 73,000 births, a record high of 1.58 million deaths in the previous year, despite a significant 11% increase in foreign residents. The overall population trend continues downward. There are also some factors like poor job prospects, high living costs, and gender-biased corporate culture affecting younger Japanese decisions on marriage and childbirth. Japan recorded an all-time low of 727,277 births, leading to a significant natural population decline.
Now, let's go to the task 2, which involves evaluating a definite integrals numerically by using a trapezoidal rule. We are asked to evaluate this following equation.
So these are the trapezoidal rule formula, which is the definite integral f of x with respect to s from a to b is equal to h over 2, where h is equal to b minus a over n, and then we multiply by y0 plus 2y1 plus 2y2 until plus yn, where n is the number of sub-interval.
So right now I'll be showing to you guys on how we solve our task 2 using trapezoidal rule. So firstly, we will write the equal sign of n6. So the equal sign are being used because we want to let the Excel to know that the formula is being used, and it will given back the exact same value of 2 in the n6 cell. However, for the fx, we also need to create a formula based on the standard operators that will be understood by the Excel. But there will be a difference when we are creating a formula of second x values, because we are adding a dollar sign between the n9 cell. So the dollar sign are being added because we want to let the Excel to refer back to the formula rather than us having to add up all the x values with the 0.7 one by one. And we just copy it down the row, and we will get all the x value. And we also need to copy down the fx down the row to get all the values. So we also need to do the same thing for the row of coefficient times fx, and we will get all the values down the row. But there will be a difference when it comes to the total, because you are using the sum of u5 colon u10. So the colon sign is actually being used because we want to let the Excel know that we want it to sum up all the u5 values until u10 to get the exact value.
So we already know how to interrogate using trapezoidal rule in Excel. Now, we back to the question. We need to evaluate the equation with 5 sub-intervals. First, we need to find our h, which is 11 over 2 minus 2 divided by 5, and we got 7 over 10. Next, we need to find our total of coefficient multiplied by fx, which is we got 36.2204937. Now, we substitute the value to the formula to find the approximate value of the area under the curve. And we got the area is 12.6771728. It is the graph of 5 sub-intervals. So now we will do for 9 sub-intervals. To repeat the step same as 5 sub-intervals, which we need to find our h value first. So 11 over 2 minus 2 and divide by 9, and we got 0.388889. Next, the sum of coefficient multiplied by x is 16.5.01838C19. After that, we substitute the value to the formula, and we got the area is 12.6424640. And this is the graph of interval 9, which they have 9 trapezium under the graph.